Greetings, friend. I will show you my favorite Sudoku trick that will reduce this puzzle by my Friday featured setter to only one advanced strategy. Click below if you want to give it a go. And with that, it's solving time. All right, to set this puzzle up, there is a few little things you need to add to it to make it the right setup. Okay, we got these sixes, column 1 and row 1 makes the sixes in two spots here. This is called Snyder notation. Anytime in a 3x3 block, you have two possibilities for a candidate. You can mark it in case you solve one of these cells. You can solve the other one right away. These sixes also act as a pointing pair. And so since they have to be in block 1 somewhere and they're limited to row 3, they cannot be anywhere else along that row. So that means sixes can't be there. They can be here, and they can now down here in block 6 with these two sixes, they can be here. And so what you notice is now the sixes are kind of like this mini X-wing. So now they're restricted to column 7 and 9 in blocks 3 and block 6. So that means that the only place where 6 can be in block 9 is in column 8 because it can't be in any of these spots. Okay, so we set up a lot of those sixes. Now, if you're working on this, you notice there's a 3, 4 in row 2, and there's 3, 4 up here in column 8. The 3, 4 are limited to these two spots, and so I'll mark that as a hidden pair. Since the 3 and 4 have to be somewhere here in block 3, limited to these two spots, no other candidates can be in those two cells. You can do the same thing over here in block 2 with the 1s and 2s. You got a 1, 2 here. You got a 1, 2 here. The only spot you can put a 1 and 2 in block 2 are right there. You thought, this might help you out with the solve. It helps later. It doesn't help right away, but we do want to mark those spots. And then you got this 9 cutting across. You got this 9 coming up. So the 9s are limited to 2 spots in block 4. Makes them a pointing pair. So they can't be here. 9's got to be in one of these spots. Okay? And then 4s, since they cut across here and they can't be in these two cells, they become a pointing pair. That's where the 1 and 2 come in handy right now. And so the 4s are limited to these two spots. They can't be anywhere else down column 4. I'll show you where that comes into play. One of the things it does is now it restricts what can be in this cell. This cell can't be a 1, 2, 3. It can't be a 4 because of the pointing pair. It could be a 5 or a 6, but it can't be a 7, 8, or 9. Okay. And if you look in this cell right here, this can't be a 1, 2, 3, 4. It can be a 5 or a 6, but it can't be a 7, 8, or a 9. They all see the cell. So you have a nice little naked pair 5, 6 right here, which limits these three cells now to a 1, 3, 4 naked pair, right? Because 5, 6 can't be in those cells anymore. You can get rid of the 3 from there. You can get rid of the 4 from there. I wanted to point that out. So all these are nice little setups, but you notice we haven't solved a cell yet. And it's pretty hard to solve one cell here, but I'm going to show you that neat little trick. And you might notice, and what I popped out to me when I first saw this, is the way the digits were set up in rows 2 and 6. And I mainly thought of my favorite trick. And so to set this up, let's see what could be in these two rows. Okay, this can't be a 6 or 9, but it can be a 1, 2, 3, 4 cutting across. Can't have 5, 6 here. Can't have an 8 there. You can't have 7, 8 there, and you can't have a 7, 8, 9 there. Okay, let's look across row 2. Looks like 2, 7, 6, 7, 8, 9, right? 6, 7, 8, 9. This can't be a 6 or a 9. Okay. You can't have the 6s here. Can't have an 8 there. All right. And you look here, can't have a 2, you can't have 7, and you can't have a 9. Okay. And then you can't have a 7, 8, 9. Okay, so we got some BVCs going on here, and we want to further restrict these cells. How can we do that? Well, let's mark all the rows that contain 1, 2, 3, 4. Let's mark all those rows up. And we're going to color them blue. All right. Then let's cover the rest of the columns with the remaining digits that we can see here. You got predominantly 1, 2, 3, 4 in the blue, and you see a lot of 6, 7, 8, 9. And what I'm about to mark here. Okay. And we're going to remove all these funky colors here where there's double colors. You don't need that. And I'll explain that to you in a second. This is my favorite trick. And this is really, really cool. So what we know is that in the blue, these rows, that contains a set of the digits 1 through 9. And so row 2, 6, 7, and 8 all contains, one set of the digits 1 through 9. So we have 4 sets of that. So the blue set, the blue group, contains 4 sets of digits 1 through 9. If you look at the orange, there's 5 of these columns that I marked. So they would contain 5 sets of the digits 1 through 9. So what I'm going to use is called Set Equivalency Theory. And what it helps us do is figure out, of these digits that are in the orange, where can they be in the blue? So what we know is that whatever we have an intersection, like these cells, they're going to be the same in the blue group as they are in the orange group. And so we don't need to worry about those. So they're going to be the same. And then you notice there's some digits that's blue and orange. You can remove those because this blue digit here will be represented by the orange right there. This orange digit can be represented by the blue right there. So we can find a spot for those. And then with these 5s, same thing. You don't want to worry about those. What we did, though, is we created this huge restriction right here. There's only 5 cells in the blue we don't know about. And they have to be and contain, since these are only 1, 2, 3s, and 4s, they got to contain some combination of these 6, 7s, 8s, and 9s. It's a little unfair, though, because if you count all these digits, you get 1, 2, 3, 4, 5, 6, 7, 8. Well, there's 8 of those. You can't fit 8 into 5. What's going on? Well, remember, we have 5 sets in the orange group and only 4 in the blue. So to even things out, if we grab from that 5th set the 6, 7, 8, 9 extra, because we're looking at a set of digits 6, 7, 8, 9 here, and then in blue looking at digits 1 through 4. So if we grab this extra 6, 7, 8, 9, remove it, then that means in 4 of the sets of the orange, that would be equivalent to these 4 sets in the blue. And so what we know is now these 4 digits, the 2 6s, the 8 and the 9, have got to be somewhere here in these 5 cells. They have to be. Plus, we have another digit. We don't know what that 5th digit is. This is what makes this puzzle so intriguing. You think, well, we can't figure this out because we have this extra digit. It could be 1 through 9. That's not going to help us, Timberlake. But it is, because there's got to be 2 6s and only 1 9. You're going to see quite a bit of restriction here. The 9's got to be in one of those spots. The 6s, they got it. One of them's got to, could be in here, or they could both be in those 2 spots. Let's see what goes on here. So if you have a 1, 2, 3, you can't have a 4 in that cell because of these 4s. You can have a 5, 6, or 9 in this cell right here. Could this be a 5? This is what you got to ask yourself. If this is a 5, then you know that since there's 2 6s in these cells, one of those 6s is going to have to be here. Actually, it would have to be there, because if you put a 6 here and blocked it out, you don't have another place to put the other 6. The 6s would have to be in those 2 spots. The problem comes in is, where would you put the 9 in the blue? We know at least 1 9's in the blue. And since now you've took these 2 cells where the 9 could be, 9 can't be blue. So we know this cell here can't be a 5. It can only be a 6 or a 9. If you put a 9 there, that's cool, because then you could put the 6 here and here. If you put a 6 here, then you could put the 9 there, and you could put the 6 in one of these spots. So we're good. The 6, 9 has to be there. This is the first big deduction you got to make. Now we come over here to this cell. What can we deduce about this cell? Well, we know it can't be a 1, 2, 3, or 4, or a 7. It could be a 5, 6, 8, or 9. Same issue goes on here, though. If we try to put a 5 or an 8 here, let's say, we put a 5 there. Now we know we got to have 2 6s over here So one of these, this would have to be a 6. And then you put a 6 in one of these two cells. Well, where does a 9 go? 9 can't go in those cells. You block it out. Same thing, if you put a 9 there, you'd have to put 2 6s in these 3 cells. We can't do it. So we know the 5 can't be there, and it's the same thing. You put the 8 there, same thing. It crams one of these, 6 or 9 in there, and then the other one won't be able to fit in those blue cells. This is awesome. I've not seen an application set done like this. What it gives us is that we can eliminate the 5 and the 8. And you can go further on and go that you can have exactly 1 6 and 1 9, because one of the 9s has to be here. It can't both be 9s, because then you wouldn't have a spot for your 2 6s. And they can't both be 6s, because you'd have no spot for your 9. So it's got to be 1 6 and 1 9. And this is exciting stuff, because we're going to be able to make some solves. And so I asked Awedish about this puzzle, how long does it take you to set Sudokus? And answer is anywhere between 3 and 20 hours to set. Wow, that's a lot of time on a puzzle, depending on uniqueness and the difficulty. He really wants it to be good quality, and I've noticed that. He'll test and rework stuff to make it even better. And he says normally for a classic, that's 6 to 7 hours, a little bit more for some of those variants. He's just got to have an idea to work with first. Well, I love the idea that you put into this. I also love the ideas that some of my great creators of puzzle packs put into their puzzle packs. So if you want to get my latest puzzle pack, you got to be a member of the Smarty Party. Click on the pin comment below and join, and you'll be supporting me to make better content, and you're investing in the future of smart hobbies. All right, I want to get rid of these extra blue and orange because we don't need the rest of this. We're not going to figure out what goes in the orange. We're just going to figure out and remember that those 5 cells have got to contain 1 6 1 9. So you got a 6 8 and some other digit in here. That's what we got to remember. This is interesting stuff. First thing we do, since we removed an 8 from this cell, and you have this 8 covering those cells, 8's got to be in one of these cells. Here in block 9, it's a pointing pair. 8 can't be anywhere else along column 7. So we can remove an 8 from right here and solve that now for a 6, which allows us to solve this cell for a 2. And we're going to be able to remove this Snyder mark and solve this cell for a 6. Awesome. All right, after solving that 6, you'll notice now 7 in this pointing pair of 8s, and this 8 and 7 limits 7 8 to these 2 cells. And so then we have a 7 8 hidden pair and a 1 3 5 naked pair right there. Okay, and now with this 2, you can remove these 2s, and you end up with this nice 7 9 naked pair. Okay, and so you have a naked pair 7 9 here in column 6. What does that do for us? Well, since the 7's got to be one of these 2 cells, it can't be in those cells. And you have these 2 7s, we can solve for 7 right there. Nice. And now you remove the 7s from here. Now you have an 8 9 naked pair in this column. And so the 9 has got to be either here and here or here and here, right? A 9's got to be one part of this naked pair in these 2 columns. So a 9 can't be in these cells anymore. This now has to be your 9. And by using that set equivalence theory, we can solve this for our 6. We know that's got to be the 6, which gives us the 5 here and the 6 here. Then remember, using this 6, now we can solve a 6 here. This has got to be an 8 and some other digit that we don't know about. But remember, there is still an advanced strategy. All this is going to reduce us to one advanced strategy. And we got a little bit of time before we get there. You got to keep watching. And you love solving puzzles like this, then subscribe to Smart Hobbies. Share us with someone you know who you think will enjoy it as well. Let's get rid of these colors because we won't need that. I'm just going to mark these at 8's got to be in one of those 2 cells. Since they have to be one of those 2 cells, the set equivalence theory, this can no longer be an 8. And so this has to be your 8. And now with this 9 and this 9, we can solve for a 9 here, which gives us a 1 4 naked pair. Awesome. And the 1 4 naked pair gets rid of the 1 right here. And wait for it, because these 4s, you can eliminate the 4 from right here, and you get 3 in the corner. Yes, there we go. All right, and now you got your 4 right here, which displaces the Snyder 4 and allows us to solve for 4 right there. Awesome. And now what you can see is with this 5, the only place left for a 5 in block 3 is right there, which gives us a 2, 9 naked pair. And with this 4, we can work our way down this column. Okay, we need a 4, we need a 5, 7, 8. I got a 5, 8 here, so that's got to be your 7. And then got to be a 5, 8 there. Well, with this 3, this is going to be your 5. It gives us a 1, 3 there. This now has to be the 8, and that's going to be your 5. And with this 8, that's a 7, and that's the 8. So we just did all that great solving there. Awesome. And now with this 8, you're going to unravel a few more solved cells. That's a 9, that's a 7, that's an 8. And now with the 5 and the 8, this is a 7. Here's your 9, here's your 8. So we solved all of that. We're not done yet. We still got an advanced trait that's going to block our path to get through this whole puzzle. But we just solved so much stuff now. All right. With this 5, where can a 5 be down here in block 8? The 5's got to be right there, right? And now, after solving that 5, let's look with these 2's. We can solve for 2 right here. Nice. With this 6, displace that Snyder 6, solve for 6 right there. Looking good. Awesome. And now we got this 7 and these 2 7s. We can solve for a 7 here. With these 2's, we can solve for a 2 here, displacing that Snyder 9. Okay. And what you'll notice is we got a 1, 4 remaining here. And this is the spot where you're going to get a little stuck. All right, if you keep going in row 5 here, this cell can be a 1, 3, 4, right? We got a 1, 3, 4 naked triple across row 5. If you come down here to row 9, you'll notice that the 4's are limited to 2 spots there, right? And the 4's are limited to 2 spots in row 5. But in row 5 and row 9, they share the same column, column 5. The tips are in different columns, but in the same 3-block band. Let me mark that up. And so what we know that these are a conjugate pair. Either this is a 4, if that's not a 4, that's got to be a 4. Conjugate pair. So either this is a 4, and anything that sees it can't be a 4. So this cell cannot be a 4. It's not a 4, this cell has to be a 4. It's the only other spot in row 5 for a 4, which knocks a 4 from here and makes this cell a 4. So if this is a 4, anything that sees it can't be a 4. If it's not, this has to be a 4. They both could be 4s, but now we know since one of these has to be a 4, we can eliminate a 4 from any cell that sees both. This is a Sudoku skyscraper. This is the only advanced strategy that you need to solve this puzzle, if you know my favorite trick. And what it does is it eliminates a 4 from right here and eliminates a 4 from right there. And since you have a 4 here, the only other place to put a 4 is right there, and then this has to be your 1. You want to learn more about skyscrapers? Check out this tutorial. But what we can do is now solve this for a 4, which makes this a 1. That's a 3, that's a 1, that's a 3. Awesome. And then what do you have here? It looks like we need a 2 or a 4. And we'll get to that. What we can do is we can eliminate the 3 from right there, which makes this now a 3. Awesome. All right. And then what we got here is, I said the 2, 4. Boom. And then we move on. And then this one, now we put a 4 right there. So there's actually a 4 in both of those. And then this is going to be your 1. And with this 3, that's got to be your 3. That's got to be your 4. Let's get rid of these colors. Thank you so much, Skyscraper, for helping us out with this puzzle. And with this 4, now that's a 1. That is your 4. And with this 4, this is a 2. That's a 4. That's a 2. That's a 1. This is a 9. This is a 2. I love to disambiguate those BVCs. Okay, what we're looking for here looks like a 1 and a 3. Got my 3 there. So here's your 3. Here's your 1. With these 2 1s, this has to be the 1. I need a 5, 8 here. Here's my 5. So here's your 5, and here's your 8. And with these 2 8s, we know this has got to be your 8. With this 9, this has to be your 9, and the last cell is a 5. Set equivalence theory has some other fascinating applications, like in this video. Please support me through my Buy Me a Coffee page. I'd really appreciate it. Thank you, Awedish, for this wonderful Sudoku, and thank you so much for watching.